In today's session, we'll understand the principle of operation of DC motors as well as of DC generators. Firstly, let's start with DC generators. Let's take the case let's take this circuit diagram. We can see a coil uh, A, B, C, D is placed in a magnetic field. We have coil A, B, C, D that's placed in a magnetic field. Uh, we understand that in case of a DC generator, what happens is that the coil is rotating in a magnetic field, and by known laws of electromagnetic induction, we understand that current will be induced uh, in these coils. A voltage will be induced in these coils that will establish the current in the coils as well. So what happens here is we have the field windings of the DC generator. We energize the the field windings. By energizing the field windings, I mean we supply the DC voltage to these field windings. As shown, as we discussed the construction in the last session, we understood there are the field windings and there are the armature windings. Field windings are placed on the poles. Uh, they are bound on the poles faces, uh, and due to the nature of winding, we can either uh, produce a north pole or we can produce a south pole, depending upon the type of winding, whether it's wound clockwise or anti-clockwise. The current flowing will be either clockwise or anti-clockwise. Accordingly, the poles produced will be either north poles or south pole. Now let's take a case where we have only two poles, that's a north pole and a south pole. So we are supplying the DC voltage to the field windings, and it produces a north pole and a south pole. The armature windings are uh, the armature windings are supported on the armature core. Uh, now, now, uh, in order to establish energy or in order to induce EMF in these conductors, we have to make sure that the armature is moving. So mechanical energy will be supplied to the armature core so that these windings uh, actually start rotating with respect to the field. In case of induction motors, the case was that we, in case of induction motors, a rotating magnetic field was produced uh, around the conductors while the conductors were still at standstill. In uh, Accordingly, an EMF was induced in the conductors. But in case of DC machines, the magnetic field produced is not rotating in nature. We have to understand that a DC current will not change direction. The magnitude of magnetic field will not be changing. As well, we can understand that there is no concept of two phases or three phases in case of DC. So we can say virtually this is only a single phase which is carrying a DC current. There is no magnitude variation. So a constant magnetic field will be produced by a DC voltage, and we can show the direction of those field from north to south. Now, since the magnetic field is constant, we need to make sure that a mechanical energy is supplied to the armature so that it rotates, such that armature starts rotating with respect to the field, and an EMF will be induced in these windings as the armature starts rotating, as per the general equation E is equal to VBL cos theta, where V will be the velocity of rotation, or we can say the angular velocity of rotation of the conductors, B is the magnetic field, and L is the length of the coil. Now we need to also understand that uh, say for example, the CD part of the coil right now is under the influence of south pole. So in this case, let's assume that the EMF induced is in this EMF induced will generate a voltage having a polarity positive here and a negative here. Accordingly, in this side, the EMF induced will have a positive here and a negative here since it is under the influence of a north pole. Now, this is at this moment of time. Now, after 180-degree rotation, once this conductor rotates by 180 degrees, now CD part of the coil will be here. That means C will be here, D will be here, and AB will now shift to this direction. We can see now because now CD is under the north pole, positive voltage will be applied here and a negative voltage will be applied here. Accordingly, positive voltage will be applied here and negative voltage will be applied here as it's under the influence of south pole. So we can see in the first instance at omega t equal to 0 degrees, D was having a polarity of plus. In after 180-degree rotation, D will have a polarity that is minus. Similarly, you can see that A was having initially the polarity minus, now it's having a polarity of plus. That means in these conductors, as it is rotating, an AC voltage is induced, not a DC voltage is induced in the conductor. So this voltage will be actually representing an AC voltage. I can also understand it from the fact that it is associated with cos component. So it's a sinusoidally varying voltage. That means this voltage will be AC in nature. So the voltage induced in the conductors ABCD is AC. As the conductor C AB is under the influence of north pole, positive polarity is induced, for example, and when it comes under the influence of south pole, a negative polarity is induced. So the voltage that we are receiving, the voltage that is generated in the armature windings is AC in nature. It is not a DC voltage. That's why we use the commutator and brush arrangement so that we can rectify the AC voltage to DC. So the commutators and brushes, they only are meant to, they are act like a rectifier in this case that will convert the AC voltage into a DC voltage. Uh, what happens is that, so if these are commutator segment, say for example, this commutator segment is attached to the coil side AB, and this commutator segment is attached to the coil side BC. Now the commutator is also rotating with the commutator is also rotating. So in this commutator segment, say initially the voltage was positive as it was under the influence of north pole. Now this commutator after 180-degree rotation moves here. That means now it will have a negative polarity. This commutator segment was initially having a negative polarity. Now after 180-degree rotation, the commutator segment will move here. That means now it will have a positive polarity. So whatever is the case, as soon the commutator moves at this end under the influence of north pole, the polarity here will be positive. Now these brushes, they are fixed. They are not rotating with the commutator. So the brush will always be carrying the same polarity. If a positive polarity is applied here, it will be carrying a positive polarity current. If a negative polarity is applied here, it will be carrying a negative polarity current. The commutators are rotating, so the commutator segments will also be carrying AC voltage, but since they are rotating, they will when they are carrying positive polarity, they will be on the top side. When they are carrying the negative polarity, they will be on the down side. That means the brushes always will be carrying the same polarity, either positive or negative. So the commutator is rotating, the brushes are fixed, uh, and by the combination of these two, by the arrangement of these two, we are able to get DC voltage at this end. Now we can be now since this is a generator, we can have some load here. Accordingly, our current will be flowing in this. Uh, Accordingly, DC current will be flowing to the load as well. So the voltage that we'll be getting from the brush will be something like this. Just like we have the same type of receive the same type of voltage from the same type of voltage is also generated using a DC diode bridge rectifiers. An AC voltage is converted into a DC voltage, a rectified DC voltage, uh, and by using proper uh, this is just an illustration here. Now, uh, how long the duration of this conductor will be under the influence of south pole, that will actually determine the peak of this sinusoidal waveform. Either it will be something like this, or it will be something like this, or it can be even like this. So it depends upon the velocity of rotation as well as the time CD takes CD. The coil conductor remains under the influence of a particular pole. So this is the operation principle of a DC generator. We energize the field windings using a DC voltage. We supply a mechanical energy to the armature core such that the conductor starts rotating. So so in presence of a magnetic field, a rotating conductor is we have a rotating conductor in presence of a magnetic field, so an EMF will be induced in these conductors. Now, since one conductor, each part of this coil it can be called as a conductor. So we can say CD is a conductor, AB is a conductor here. So AB conductor remains under the influence of north pole for 180 degrees, and for it remains under the influence of south pole for another 180 degrees. So either a positive polarity will be induced in AB or a negative polarity will be induced in AB as it changes as it starts rotating. So an AC voltage is generated in the conductors, but because of the arrangement of commutator and brush, where commutators are rotating and the brush are kept fixed, we are able to receive a DC voltage, and this DC voltage will be somewhat similar to that of diode bridge rectifier. Now this is the simple operating principle. Uh, so the voltage that the DC voltage that will be obtaining from this DC generator, we'll be studying that later after we study actually lap winding and wave winding. Now we'll move on to the DC motor operating principle. Assume the same circuit diagram. Now, in case of DC motor, what happens is we are supplying DC voltage to the field winding as well as DC voltage is supplied to the armature winding. The field windings will produce a north pole and a south pole as shown here, and in this case we will be supplying the armature with DC voltage as well. What happens is the armature again, because of the commutators and brush arrangement, now this will act as an inverter here. Now the DC voltage will be converted into AC. So the conductors will now be carrying AC current. Now we have a current carrying coil placed in a magnetic field, and from we understand from magnetic electromagnetic principles that when a current carrying conductor is placed in a magnetic field, it will experience a torque. As it experiences a torque, it will start rotating. So the principle of operation is simple. We are energizing the field windings. They will produce a north pole and a south pole. We are energizing the armature also in this case using a DC voltage. Now the brush and commutators will act as an inverter here, and they will the current available at this point will be AC in nature. So the conductors will still be carrying AC currents. Now a current carrying coil is placed in the magnetic field. They will experience uh, torque, and that's given by BIL sine theta. So this is the simple operating principle. Now we need to understand something else. Uh, Now once this conductor starts rotating, we can see that this conductor is rotating now. The magnetic field is still present. Fine. So if we have uh, a conductor rotating in a magnetic field, we can say that EMF will be induced in these conductors. That means the initial operation was of a motoring mode, wherein we were energizing the armature as well as the field using a DC voltage. A current carrying a conductor was placed in a magnetic field and it started rotating because of the torque produced in it. Now, since we have a rotating conductor placed in a magnetic field, so naturally EMF will be induced in this. So, this EMF will now act in a counterclockwise direction. So, that means an EMF is induced in the armature conductors, but already the armature is being supplied from this DC voltage source that's uh, uh, located externally. So the EMF induced now in these conductor will start opposing the armature voltage that is being applied. So this EMF that opposes the actual armature voltage, that was the actual cause of generation of this EMF voltage in the first instance, is known as the back EMF. Now, this back EMF will actually what happens is now because an EMF is also induced in these conductors, this back EMF will oppose the DC voltage that's being applied to the armature. So, the net voltage that will be available across the armatures will be VDC minus V back EMF. So, there are other types of losses also that we'll be studying later on. So right now we need to understand that how a back EMF is produced. It's a simple phenomenon. We have a rotating conductor now in a magnetic field, so an EMF will be induced. And since this EMF is induced in a direction that's opposite to that of the actual voltage that was causing it, so the net voltage will be VDC minus VB. So what back EMF is? It is the voltage that is generated because of the rotation of the conductor in a magnetic field. So in case of DC motors, a back EMF is produced in the armature conductors that will oppose the actual armature voltage being applied to the DC motor in the first instance. So this back EMF, now what is it dependent upon? We know that induced EMF is equal to VBL. Since B and L cannot change, we can assume that E will be proportional to the velocity of rotation. So, if the DC motor is rotating at a slower speed, the back EMF induced will be less. If the DC motor is rotating at a higher speed, the back EMF induced will be more. So, depending upon uh, the speed of rotation of this armature, the back EMF will accordingly, the magnitude of back EMF is dependent upon the velocity of rotation of the armature. E is directly proportional to omega. Uh, so this is the principle of DC motor. We energize the field winding, we energize the armature winding. Current carrying conductor in a magnetic field will experience a torque given by the equation BIL sine theta. Now, since a conductor is rotating in a magnetic field, that means an EMF will be induced in these conductors. Now, this EMF induced will be actually opposing the uh, cause of its generation, that is VDC in this case. So, the net voltage available across the armature conductors will be VDC minus VB. Uh, Also, we understand that EMF induced is equal to VBL cos theta. Here, the magnetic field will not change since the field windings will be provided with a constant DC voltage source. The length of the conductor cannot change. The velocity of the conductor can change. So, if the DC motor is rotating at a higher speed, the back EMF will be larger. If DC motor is rotating at a smaller speed, at a lesser speed, the back EMF induced will be lesser. Accordingly, the voltage available across the armatures will be decided. So this is a simple principle of operation of DC generators and DC motors. Now, after understanding the types of windings, lap winding and wave winding, we'll be able to uh, will be uh, deriving the equation of induced voltage in case of DC generators. That we'll do in the next session.